This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. As easy as current sources are, they do come with some strings attached. The most important being that current sources cannot violate basic series and parallel properties, nor establish laws like Kirchhoff's voltage law or Kirchhoff's current law. Here are two rules and regulations regarding current sources. Rule 1. Current sources of different magnitudes can never be placed in series with one another. This doesn't make sense. If source 1 pushes 30 mA through the circuit regardless of applied load, and source 2 pushes 50 mA through the same circuit regardless of applied load, this won't work out well because current through elements in series is the same. Last time I checked, 30 doesn't equal 50, nor does 50 equal 30. This being said, current sources of different magnitudes can be placed in parallel with one another. If source 1 pushes 30 mA through the circuit and source 2 pushes an additional 50 mA through the circuit, what's the total current delivered to the circuit? The answer via Kirchhoff's current law is 30 plus 50, or 80 mA. Makes sense. Now here's where reality steps in. What's the voltage across current source 1? What's the voltage across current source 2? Don't think too hard because I hate for your head to explode. If voltage across elements in parallel is the same, this is where we must necessarily make a simplification of our simplification. Rule 2, current sources in parallel add up. There is now a single 80 mA current source. If our load resistor is 390 ohms, the voltage across it via Ohm's law would be 31.2 volts. Before we bring this short lecture to a close, let's pause to consider the means of operation and limitations of real-world current sources. As I mentioned at the beginning of this lecture, if you crack open a current source, what you'll find is actually a variable voltage source that continually monitors and maintains output current at some constant value. The means of doing this is via a closed-loop controller, one of the more basic elements of control theory. A closed-loop controller requires two basic inputs. One, some desired set point established by an operator. In this case, output current, which an operator wants to maintain at 80 mA. Two, a means of monitoring the actual output of the system. In this case, an ammeter could be used to measure actual current produced by the source. The controller continually compares the desired set point with the actual output of the system. If there's a difference between the desired output and the actual output, there's an error, and the polarity and magnitude of the error represents by how much the system must increase or decrease its output to achieve the desired set point. Consider the inner workings of the current source supplying 80 mA to a 390 ohm resistor. The desired set point is 80 mA. The actual output is 80 mA. The error is 0 mA, and the adjustable voltage supply continues to supply our previously calculated 31.2 volts, sufficient to push the desired amount of 80 mA through the 390 ohm load resistor. If, however, the load resistor increased to 470 ohms, an application of Ohm's law demonstrates that 31.2 volts would push only roughly 66.4 mA of current through the system. Via the feedback loop, the current source realizes there is an error of 13.6 mA, and because of the sign associated with the summing junction, realizes the set point is higher than the output and must increase its output by an additional 13.6 mA. Via the transfer function, a bit of control theory math I'm skipping over right now, that for this circuit is kind of just like Ohm's law in a nice suit and tie, the adjustable voltage source increases its output to 37.6 volts. At this voltage, current again returns to 80 mA and the error is 0 mA. Does this happen instantly? No. There's some appreciable rise time and there's some overshoot and settling over time. We'll learn in much later lectures all the dirty details and secret tricks of control theory, but for now, consider this most basic of introductions. Two more quick examples though, and our brief tour will be complete. Let's say the load resistor dramatically drops to 180 ohms. An application of Ohm's law demonstrates the present level of 37.6 volts would push 208.9 mA of current through the system. This is clearly in excess of the desired 80 mA set point. The error in this case is 128.9 mA. The error output is telling the voltage source to take a log off that fire. Another application of Ohm's law demonstrates that the voltage source needs to drop to 14.4 volts. and the current source will return to supplying 80 milliamperes, where again the error between the actual output and the desired set point is 0. Finally, let's say the load resistor is dramatically increased to 2 kiloohms. At the present level of 14.4 volts, an application of Ohm's law demonstrates that only 7.2 milliamperes of current travels through this system. This is way below the desired 80 milliampere set point. The error in this case is 72.8 milliamperes. The large amount of error is saying hit the gas and hit it hard. The output voltage rises and rises, but at some point, a real-world current source, in contrast to the mathematically perfect entities we've just discussed, is just going to run out of steam. An application of Ohm's law demonstrates a voltage of 160 volts would be required to push 80 milliamperes of current through the 2 kilo ohm resistor. But let's say the adjustable voltage source inside this real-world current source tops out at a maximum of 120 volts. An application of Ohm's law demonstrates that 120 volts supplying a 2 kilo ohm resistor delivers only 60 milliamperes of current. There's still a 20 milliampere error between the desired set point and the actual output, but the real world has hard limits that real devices just can't surmount. Long story short, if you're using a benchtop power supply as a current source, know its operational range and simply operate inside that range. Inside the operational range, the current source should push the required amount of current through whatever you throw at it. Outside the operational range, expect to reach some peak performance, followed by a predictable decline. Okay, I think we've delivered a sufficient introduction to the current source. Keep in mind we'll be seeing the current source again in later circuit analysis scenarios, as well as making use of a handy equivalency between current source and voltage source configurations called source conversion. Remember, never place current sources of different magnitudes in series with one another, and current sources in parallel add up. Stay on the right side of Kirchhoff's laws. Believe me, the judgments are swift and the punishments are harsh. In conclusion, this lecture presented the current source and examined circuit analysis scenarios employing DC current sources. Additionally, we discussed the rules regarding current sources in series and parallel. Finally, we presented the inner workings and limitations of real-world current sources. Remember to review these materials as often as you need to really drive it home. Imagine how well that will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lad partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.